All right, today we're going to dive into a technology that's completely rewriting the rules for how we make, well, pretty much everything. We're talking about polymer 3D printing. From custom car parts to medical implants made just for you, this field is moving at lightning speed. So, let's get right into it.
But first, let me ask you something. How do you actually build the impossible? You know, a part that has channels twisting and turning on the inside, or a prosthetic that fits a person's body like a glove, or just a really complex object that's made in one single piece, with no seams, no bolts, nothing?
For a really long time, a question like that was pure science fiction, but not anymore. Today, the answer is additive manufacturing, which we all know as 3D printing. It's this incredible technology that literally builds objects from the ground up, layer by tiny layer, straight from a digital design file.
Think about it. For centuries, the only way we made things was by subtracting. You know, carving, cutting, or drilling material away from a big solid block. Kind of like a sculptor carving a statue out of marble. And hey, it works, but it can be super wasteful. Additive manufacturing just flips that whole idea on its head. It adds material only where you need it, building things layer by layer, almost like you're using digital Legos. This way is not just way more efficient, but it lets us create shapes that were literally impossible to make before.
So, how does this magic actually happen? Well, there's not just one single type of 3D printing. Let's take a quick tour of the three main polymer technologies you're going to run into.
Okay, first up is the one you've probably seen before, Fused Deposition Modeling, or FDM. If you've ever seen a desktop 3D printer in a school or a library, this is almost certainly what you are looking at. The absolute easiest way to picture it? Just think of a very, very precise hot glue gun that's being controlled by a robot. So here's how it works. It starts with a big spool of plastic string, called a filament. That filament gets fed into a super hot nozzle, which melts it. Then the printer head moves around, drawing the very first layer of the object with this melted plastic. That layer cools and hardens almost instantly, and then the printer moves up just a tiny bit and draws the next layer right on top of the first. You just repeat that a few hundred, or maybe a few thousand times, and poof, you've got a solid object.
Now, the biggest plus for FDM is just how accessible it is. The technology is pretty simple, it's affordable, and you can use a massive range of different plastics. The trade-off? You can usually see the lines between each layer, and the parts are a little weaker along that vertical axis, because the bonds between the layers just aren't as strong as the plastic itself. Still, for making prototypes and for everyday use, FDM is an absolute game changer.
All right, next up we've got something totally different, VAT photopolymerization. These printers don't melt plastic at all. Instead, they start with a tank, or a vat, that's filled with a special liquid resin that has a cool property. It gets hard when you shine UV light on it.
The whole process is, well, it's just fascinating to watch. A build platform dips down so it's just barely under the surface of the liquid. Then a controlled light source, either a super precise laser for SLA or a digital projector for DLP, shines the shape of one layer onto it, and that liquid instantly turns into a solid. The platform then lifts up, a fresh layer of resin flows underneath, and the process repeats. It seriously looks like you're pulling a solid object right out of a pool of liquid. So the payoff for all that liquid magic? Incredible detail. We're talking perfectly smooth surfaces and features so tiny you'd need a microscope to see them. It's perfect for things like dental models or intricate jewelry. The downside is that the parts can be a little brittle at first and usually need a final bath in UV light. That's called post-curing, to really finish the chemical reaction and get to their maximum strength.
Our third major technology is a real industrial powerhouse, selective laser sintering, or SLS. This one is different again. It doesn't use filament, it doesn't use liquid resin, it uses a bed of super fine polymer powder, usually something like nylon. The process here is really elegant. A roller pushes a paper-thin layer of powder across a build area. Then, a high-powered laser zaps down and draws the shape of the layer, fusing, or sintering, those little powder particles together into a solid. A new layer of powder gets rolled on top, and it all happens again. But here's the really clever part. All that loose, unfused powder around the object acts as a natural support while it's printing. That means you can create ridiculously complex geometries without needing to build extra support structures.
And the result? You get parts that are incredibly strong, really durable, and ready for real-world use right out of the printer. We're talking functional parts in cars and airplanes. The catch, of course, is that the equipment is pretty expensive,
and handling all that fine powder requires some serious safety precautions. So, we've seen the printers, but what about the ink? Because the materials you use are every bit as important as the machines themselves. Let's take a look at the polymer palette.
You can see right away, thermoplastics, that's the kind you melt, are the undisputed king of the hill, making up the huge majority of plastics used in both FDM and SLS printing. The photopolymer resins, for those super high-detail printers, come in at a distant second, followed by this really cool growing category of specialty materials, like flexible elastomers and super strong composites.
And even just within thermoplastics, the variety is huge. You've got PLA, which is super easy to work with and even biodegradable, making it perfect for prototypes. Then you've got ABS. That's the same tough, impact-resistant stuff that Lego bricks are made of. And for those really high-end industrial parts, you have nylon, which is an absolute workhorse, strong and flexible. Picking the right material for the job is totally key to a successful print.
Okay, so we have the tech, we have the materials, but why does any of this actually matter? Let's look at how this technology is literally printing a new world all around us. In healthcare, the magic word is customization. I mean, just imagine a prosthetic limb that is perfectly, exactly molded to a patient's body. Or a surgeon who gets to practice a really complex operation on an exact 3D printed replica of their patient's heart before ever making a cut. The amazing thing is, this isn't science fiction. This is happening right now.
In things like airplanes and cars, every single gram counts. 3D printing lets engineers design these incredibly complex, lightweight parts that are still amazingly strong. What does that mean for you? Better fuel efficiency. And for the companies, it means they can test out new designs way faster than ever before.
And this crazy level of customization is coming to products you use every single day. Think about running shoes with a midsole that's printed specifically for your weight and your running style, or glasses frames that are designed to fit the exact contours of your face. We're moving away from an era of mass production and into an era of mass personalization.
And here's a really cool twist. 3D printing isn't just replacing old ways of manufacturing, it's actually making them better. Companies are printing custom tools, jigs, and fixtures that make their existing assembly lines faster, cheaper, and way more efficient. It's a total win-win. All of this is absolutely incredible, but the technology is still just getting started. It's constantly evolving. So let's wrap up by taking a quick look at what's just over the horizon.
One of the biggest challenges right now is sustainability. While this whole additive process creates way less waste up front, a lot of the polymers themselves can be really tough to recycle. But the good news is, this is a huge focus for researchers who are working on everything from new biodegradable filaments to more efficient recyclable powders to make the entire life cycle of a printed part greener.
So, we've seen how printing layer by tiny layer lets us build what once seemed impossible, from medical miracles to lighter and faster cars. And that really brings us to our final question for you. As this technology gets smarter, faster, and greener, and becomes as common as the paper printer on your desk, what is the one thing you wish you could bring from a digital file into the real world?